Welcome, everyone. I'm excited to start our journey today with the topic, the number system. On this first slide, you'll see the title that sets the stage for what we'll explore. We'll be looking into how numbers work, their different types, and how they form the foundation of math. This presentation will give you a clear overview of the number system, from basic concepts to more advanced ideas. So, let's dive in and discover the fascinating world of numbers together. Let's move on to slide 2. Here, we see a variety of topics and questions that build on our understanding of real numbers. First, we are asked to prove that certain numbers are irrational, which helps us understand the nature of irrationality in numbers like roots and sums involving irrational parts. Then, we look at why some specific numbers are composite, which involves understanding factors and divisibility. We also have questions about rational and irrational numbers, including proving the irrationality of expressions like 3 plus 2 times the square root of 5. Moving forward, there's a problem involving the greatest common divisor and least common multiple of two numbers, which reinforces our understanding of these concepts in number theory. We also explore famous mathematicians and their contributions, helping us appreciate the history behind these ideas. The slide includes a description of parts of the real number system, which provides a framework for categorizing different types of numbers we encounter. Furthermore, there are practical questions about decimal expansions of rational numbers, whether they terminate or repeat, and proofs of irrationality for numbers like the square root of 5. Finally, we see problems involving the least common multiple and highest common factor, Euclid's division algorithm, and real-world applications like the circular path example. All these topics connect to deepen our understanding of the properties and relationships within the real number system. Let's explore the different subsets of the real number system. First, we have irrational numbers, which are numbers that cannot be expressed as a simple fraction. They have non-repeating, non-terminating decimal expansions. Moving on, rational numbers are numbers that can be written as a fraction, where both the numerator and denominator are integers, and the denominator isn't 0. Then, we have integers, which include all whole numbers and their negatives, so -3, -2, -1, 0, 1, 2, 3, and so on. Next are whole numbers, which are similar to integers but do not include negative numbers. They start from 0 and go upwards. Finally, natural numbers are the counting numbers starting from 1 and increasing onward. The key idea here is that the real number system contains many subsets, each with its own characteristics. Importantly, all these subsets together make up the entire set of real numbers, which includes both rational and irrational numbers. Understanding these subsets helps us see the structure within the real numbers and how different types of numbers relate to each other. This foundation is crucial as we continue exploring the broader concept of the number system. Let's take a closer look at the Venn diagram of the real number system. This diagram is a great visual tool for understanding how different types of numbers relate to each other. At the center, we have the real numbers, which include pretty much everything we work with in everyday math. These are the numbers that can be found on the number line. Inside this big circle, you'll see subsets like rational numbers, which include fractions and terminating decimals, and irrational numbers, like pi or the square root of 2, which cannot be expressed as simple fractions. What's interesting is how these subsets overlap and interact, illustrating the complexity and richness of the real number system. This diagram helps us see that all rational and irrational numbers are part of the real numbers, but not all real numbers are rational or irrational. Some are both, in a way, depending on how we look at them. Understanding this relationship is key because it sets the foundation for more advanced topics, like algebra and calculus, where knowing the properties of these different number types becomes essential. So, as we move forward, keep in mind how these categories fit together, because it will help you make sense of more complex mathematical concepts and their applications in real life. Let's take a moment to understand the different types of numbers we're working with. First, we have integers, which include all the whole numbers and their opposites. So, that means negative numbers like -3, -2, -1, 0, and positive numbers like 1, 2, 3, and so on. Integers give us a complete set of whole numbers along with their negatives, which is really helpful when we're dealing with situations that involve going above and below 0. Next, we have whole numbers. These are a bit more limited. They include 0 and all the natural numbers starting from 1 onwards. So 0, 1, 2, 3, 4, 5, and so on. Whole numbers are great when we're counting objects or things that don't involve negatives. And then there are natural numbers, which are simply the counting numbers starting from 1. So 1, 2, 3, and continuing indefinitely. These are the numbers we typically use when we're counting items in a list or a sequence. Understanding these distinctions helps us see how the different sets of numbers relate to each other and form the building blocks of the real numbers. This foundation is essential as we explore their properties and how they fit into the broader number system. Let's take a look at some examples of irrational numbers. For instance, numbers like 0.34334333433334 or 45.86745893. These are non-terminating, non-repeating decimals, which means they go on forever without ever settling into a pattern. A famous example is pi, or pi, which is also irrational. These numbers can't be written as simple fractions, and their decimal expansion just keeps going without repeating. On the other hand, we have rational numbers. Examples like 36.8, 0.125, or 4.5 are rational because they can always be expressed as either terminating decimals or repeating decimals. That means you can write them as fractions, like 36.8 as 368/10, or 0.125 as 1/8. Now, to clarify the key difference, irrational numbers are any numbers that cannot be written in the form of a fraction where both numerator and denominator are integers, with the denominator not equal to 0. So, irrational numbers are those that can't be expressed as a simple fraction. Rational numbers, however, are numbers that can be written in that fractional form, like a b, where a and b are integers and b isn't 0. This distinction helps us understand the structure of real numbers and how they fit into our broader number system. In summary, rational numbers are those we can neatly write as fractions, while irrational numbers are the ones that defy that, with decimal expansions that go on forever without repeating. This distinction is fundamental to understanding the nature of different types of numbers in mathematics. Let's take a closer look at what this slide is telling us. When we have two positive integers, which we'll call a and b, there's a special relationship involving two other integers, q and r. These are unique, meaning there's only one such pair that fits the description. The key equation is a equals b times q, plus r. Now, the important part is the condition on r, which has to be greater than 0 but less than b. This is essentially the foundation of Euclid's division algorithm. It helps us understand how any number can be expressed in terms of division and a remainder. This concept is fundamental because it underpins many other ideas in number theory, like finding the greatest common divisor. And as we progress, you'll see how this simple but powerful concept can be applied to more complex problems. Now the HCF is 4. We consider the new divisor 24 and the new remainder 4, and apply the division lemma to get 24 equals 4 times 6 plus 0. Next, we look at the new divisor 124 and the new remainder 24, and again apply the division lemma. 124 equals 24 times 5 plus 4. Then, we consider 148 as the new divisor and 124 as the remainder, which gives us 148 equals 124 times 1 plus 24. Similarly, for 272 and 148, we find 272 equals 148 times 1 plus 124. Next, with 420 and 272, the division lemma tells us 420 equals 272 times 1 plus 148. Since the remainder 420 is not 0, we perform the division on 4052 and 420. 4052 equals 420 times 9 plus 272. Because 12,576 is greater than 4052, we next divide 12,576 by 4052, resulting in 12,576 equals 4052 times 3 plus 420. Now, to find the HCF of 4052 and 12,576, we follow these division steps, applying Euclid's division algorithm systematically. This process illustrates how the division lemma helps us break down larger numbers into smaller parts to find their greatest common divisor efficiently. In the 1870s, two influential German mathematicians, Georg Cantor and Richard Dedekind, made groundbreaking contributions to our understanding of the real numbers. They demonstrated a fundamental relationship between real numbers and points on the number line. Specifically, they showed that for every real number, there is a corresponding point on the real number line. And conversely, for every point on this line, there exists a unique real number associated with it. This might sound intuitive now, but at the time, it was a crucial step in establishing the rigorous foundation of real analysis. Their work helped us understand that the real numbers and the geometric concept of the number line are perfectly aligned, creating a solid basis for much of modern mathematics. This connection is essential as we explore how numbers can be represented and understood both algebraically and geometrically. Let's talk about the Greek genius Archimedes, who was actually the first to determine digits beyond the decimal point in the expansion of pi. He managed to show that pi is between 3.140845 and 3.142857. This was a remarkable achievement for his time and laid important groundwork for future mathematicians. Now, moving to India, Aryabhata, who lived around 456 to 550 AD, was another brilliant mathematician and astronomer. He calculated the value of pi to 4 decimal places, specifically 3.1416, which was incredibly accurate for his era. Fast forward to today, with the power of high-speed computers and sophisticated algorithms, we've pushed the boundaries even further. Pi has now been computed to over 1.24 trillion decimal places. These milestones highlight how our understanding of pi has evolved, from early approximations to incredibly precise calculations, showing the importance of mathematical innovation across different eras and cultures. Now, let's move on to the final slide, which is about questions. If you have any doubts or need further clarification on using Euclid's division algorithm to find the HCF, this is the perfect time to ask. Remember, understanding the process thoroughly is key, so don't hesitate to bring up anything that's unclear. This slide serves as an open invitation for discussion, ensuring that everyone leaves with a solid grasp of the concept. Feel free to share your questions or insights now. Since the remainder is 0, the process stops here. This indicates that the highest common factor, or HCF, of 135 and 225 is 45. Now, let's look at the next step. We consider the new divisor, which is 90, and the new remainder, which is 45. Applying the division lemma, we see that 90 equals 2 times 45 plus 0. Because the remainder is now 0, we know we've reached the end of our process. Next, since the remainder 90 is not 0, we go back and apply the division lemma to 135 and 90. This gives us 135 equals 90 times 1 plus 45. Notice how this step helps us find the common factors. And then, because 225 is greater than 135, we apply the division lemma again, this time to 225 and 135. Doing so, we get 225 equals 135 times 1 plus 90. So, to summarize, these steps, applying the division lemma repeatedly, are how we systematically find the HCF of two numbers. The key takeaway here is understanding how the remainders get smaller each time, guiding us to the greatest common divisor. As we can see here, since the remainder is 0, the process of finding the highest common factor, or HCF, comes to an end. At this stage, the divisor we are looking at is 196, which means that 196 is the HCF of 196 and 38,220. It's important to note that because 38,220 is greater than 196, we applied the division lemma to these two numbers. The division lemma allows us to express 38,220 as 196 times 195 plus 0, which confirms that 196 divides 38,220 exactly. So, in summary, the key point here is that the process of repeated division has led us to a point where the remainder is 0, and this tells us that the divisor at this step, 196, is indeed the highest common factor of the two numbers. This step is crucial because it shows how the Euclidean algorithm efficiently determines the HCF by successive division. Now, since the remainder is 0, the process comes to a stop. At this point, we see that the divisor is 51, which means that the highest common factor, or HCF, of 867 and 255 is 51. Next, we consider the new divisor, which is 102, and the new remainder, 51. Applying the division lemma here, we get 102 equals 51 times 2 plus 0. Since the remainder is not 0, we continue applying the division lemma, but now to 255 and 102. This gives us 255 equals 102 times 2 plus 51. And because 867 is greater than 255, we apply the division lemma once more, this time to 867 and 255. We find that 867 equals 255 times 3 plus 102. This process highlights how the division lemma helps us systematically find the greatest common divisor, or GCD, by breaking down the numbers step by step. It also shows the importance of the remainders reducing to 0, which signals that we've found the HCF. Now, let's look at how we can find the maximum number of columns for our parade. We have an army of 616 members and an army band of 32 members, and we want them to march in the same number of columns. The key question here is, what is the largest number of columns they can both fit into without breaking their formation? To solve this, we need to find the highest common factor, or HCF, of 616 and 32. The HCF tells us the greatest number that divides both numbers exactly, ensuring both groups can be arranged in that many columns. So we use Euclid's algorithm to find this HCF. First, we divide 616 by 32, which gives us 19 with a remainder of 8. That is, 616 equals 32 times 19 plus 8. Next, we check if 8 divides 32 evenly. Since 32 divided by 8 equals 4 with no remainder, we're done. This means the HCF of 616 and 32 is 8. And this value, 8, is crucial because it tells us that both the army and the band can march in 8 columns. It's the maximum number that divides both groups evenly, ensuring a neat, organized parade. So to recap, the HCF, calculated using Euclid's algorithm, gives us the maximum number of columns they can march in together. And in this case, that is 8 columns. So what we're seeing here is that the square of any positive integer can only take on specific forms, specifically either 3m or 3m plus 1. To understand this better, let's consider a generic positive integer, which we'll call a now. Using Euclid's division lemma, we can express a as 3q plus some remainder r, where q is an integer and r can be 0, 1, or 2. This is because when dividing by 3, the remainder must always be less than 3. Next, if we square a, we're looking at a 2, which can be written as 3q plus r2. Expanding that, we get 9q2 plus 6qr plus r2. Now, depending on whether r is 0, 1, or 2, the resulting expression simplifies differently. For r equals 0, a 2 simplifies to 9q2, which is clearly divisible by 3, so it fits the form 3 times some integer m. When r is 1, the expression becomes 9q2 plus 6q plus 1. We can factor out a 3 from the first two terms, leaving us with 3 times 3q2 plus 2q plus 1. So in this case, a 2 is of the form 3m plus 1. Similarly, when r is 2, the expression becomes 9q2 plus 12q plus 4. We can write 4 as 3 times 1 plus 1, so the entire expression simplifies to 3 times some integer plus 1 again. This analysis shows that no matter what positive integer we start with, its square will always be either divisible by 3 or leave a remainder of 1 when divided by 3. And that's exactly why we say the square of any positive integer is either of the form 3m or 3m plus 1. This conclusion follows directly from Euclid's division lemma and helps us understand the structure of squares in modular arithmetic, tying back to our overall theme of number properties. Let's look at some examples of expressing numbers as products of their prime factors. First, consider the number 5005. Its prime factorization is 5 times 7 times 11 times 13. This shows how we break down a large number into its basic building blocks, the prime numbers. Next, we have 156. When we factor it, we get 2 times 2 times 3 times 13, which can also be written as 2 squared times 3 times 13. Recognizing these patterns helps us understand the structure of numbers better. Moving on, 7429 factors into 17 times 19 times 23. Notice how these are all prime numbers, and their product gives us the original number. Prime factorization often reveals interesting relationships between numbers. Then there's 3825, which breaks down into 3 times 3 times 5 times 5 times 17. This can be expressed as 3 squared times 5 squared times 17. Seeing these repeated prime factors helps us see the multiplicity within the number. Finally, we have 140, which factors into 2 times 2 times 5 times 7, or 2 squared times 5 times 7. The key point here is that expressing numbers as products of their prime factors is a fundamental skill in number theory. It helps us understand the structure of numbers and is essential for solving many mathematical problems. Keep practicing these factorizations to strengthen your understanding of prime numbers and their properties. Let's analyze the different cases to understand the possible forms of the cube of any positive integer. First, consider the case where I equals 3q plus 2. Here, q is an integer, and m is defined as 3q cubed plus 6q squared plus 4q. So the expression becomes 9 times that m plus 8, which simplifies to 9m plus 8. Next, when I equals 3q plus 1, m is defined as 3q cubed plus 3q squared plus q. The cube of a in this case expands to 27q cubed plus 27q squared plus 9q plus 1, which simplifies to 9 times m plus 1. Now for the case where a equals 3q, m is 3q cubed, and the cube of a simplifies to 27q cubed, which is 9 times 3q cubed, giving us 9m. Putting it all together, what does this tell us? It means that the cube of any positive integer can be expressed in one of these three forms: 9m, 9m plus 1, or 9m plus 8. This classification covers all possible cases, thanks to Euclid's division lemma. So the key takeaway is that no matter what positive integer we choose, its cube will always fall into one of these three categories. This insight is fundamental because it helps us understand the structure and properties of cubes within modular arithmetic. Now let's look at the numbers 17, 23, and 29. These are interesting because they are all prime numbers. When finding the LCM and HCF of pairs involving these, the prime nature makes the process straightforward. Remember, the HCF, or highest common factor, is the greatest number that divides both numbers exactly. Since these are prime, their HCF will often be 1 unless they are the same number. The LCM, or least common multiple, is the smallest number that is a multiple of both numbers. For prime pairs, the LCM is usually the product of the two, unless they are the same prime number. Let's verify this with an example. Say, for 17 and 23, since both are prime and different, the HCF is 1. The LCM is simply 17 multiplied by 23, which gives us 391. And as a quick check, multiplying the HCF and LCM, 1 times 391 equals 391, which is exactly the product of 17 and 23. This demonstrates that for these pairs, the relationship LCM times HCF equals the product of the numbers holds true, especially when dealing with prime numbers. It's a neat property that helps us understand the fundamental relationships between numbers. Let's look at some example answers to reinforce the concepts we've been discussing. For the first one, the answer is 8, 9, and 25. These are particular numbers that fit the criteria we're examining. Moving on, the second answer is 12, 15, and 21. Again, these numbers illustrate the pattern or property we're focusing on. Now, an important point to remember here is that the product of two numbers is equal to the product of their highest common factor, or HCF, and their least common multiple, or LCM. So, whether we're working with these specific examples or others, this relationship holds true. For the next set, the answer is 510 and 92. These are two numbers whose product relates directly to their HCF and LCM, as we've just discussed. And finally, the last example shows the numbers 26 and 91. Once more, the key takeaway is that their product equals the HCF multiplied by the LCM. This principle is fundamental because it connects the concepts of HCF and LCM directly to the multiplication of the numbers themselves, which is a powerful idea to keep in mind as we move forward in our study. All right, let's take a look at this problem. We are given that the highest common factor, or HCF, of 306 and 657 is 9. Our goal here is to find the least common multiple, or LCM, of these two numbers. Now, remember, the HCF is the greatest number that divides both numbers evenly, while the LCM is the smallest number that both numbers divide into without leaving a remainder. One key point to note is that there's a direct relationship between HCF and LCM for any two numbers. Specifically, the product of the two numbers equals the product of their HCF and LCM. So, in mathematical terms, we can write 306 multiplied by 657 equals HCF of 306, and 657 times the LCM of 306 and 657. Since we already know the HCF is 9, we can substitute that into our equation. That means 306 times 657 equals 9 times the LCM. Now our task is to solve for the LCM. To do that, we'll divide both sides of the equation by 9. Doing this calculation, 306 times 657 divided by 9 gives us the value of the LCM. And that, in a nutshell, is how we find the LCM when we know the HCF. It's a straightforward process once you understand the relationship between these two concepts. Let's take a closer look at why these two expressions are considered composite numbers. First, focus on the expression 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5. When we break it down, we see that it can be factored into 5 times another expression, specifically 7 times 6 times 4 times 3 times 2 times 1 plus 1, which simplifies to 1008 plus 1, or 1009. Since 1009 is a number that cannot be factored further, the entire expression becomes a product involving 5 and 1009, making it a composite number. Similarly, look at the second expression, 7 times 11 times 13 plus 13. We can factor out 13, giving us 13 times the sum of 7 times 11 plus 1, which equals 77 plus 1, or 78. And 78 can be further broken down as 13 times 6, which shows that our original expression is divisible by numbers other than 1 and itself. This confirms that it's also a composite number. The key idea here is that a composite number is one that has factors other than 1 and itself. In both cases, we found factors, like 5, 13, and 1009, that show these numbers are not prime. Recognizing these factors helps us understand the fundamental difference between prime and composite numbers, which is essential as we explore more about number properties and their applications in mathematics. So let's look at the key points here. Ravi and Sonia start together at the same point on a circular track. Sonia takes 18 minutes to complete one round, while Ravi takes only 12 minutes for the same. Since they start at the same time and go in the same direction, the question is, when will they meet again at the starting point? To figure this out, we need to understand the concept of the least common multiple, or LCM. The LCM of their times tells us the earliest time when both of them will be back at the starting point simultaneously. Now let's see how we determine that. The prime factorization of 12 is 2 times 2 times 3, and for 18, it's 2 times 3 times 3. When we find the LCM, we take the highest powers of each prime factor, which gives us 2 times 2 times 3 times 3, or 36. This means that after 36 minutes, Ravi and Sonia will both have completed a whole number of laps and will meet again at the starting point. Since Ravi takes 12 minutes per lap, he completes 3 laps in that time, and Sonia completes 2 laps. The key takeaway here is that the total time for them to meet again at the start is the LCM of their individual lap times. In this case, it's 36 minutes, which is the minimum time when both are back at the starting point together. This idea of using the LCM helps us understand repetitive patterns and timing in circular motion, which ties into the overall theme of motion and periodicity we're exploring. So from this, we see that square root 5 cannot be expressed as a fraction p over q, which means that square root 5 is irrational. Now, this is a crucial point because it leads us to a contradiction if we assume that square root 5 is rational. If square root 5 were rational, then we could write it as a fraction a over b, where a and b are integers with no common factors other than 1. That is, they are coprime. But following the logic, if a over b equals square root 5, then squaring both sides gives us a squared over b squared equals 5. Rearranging, we get a squared equals 5 times b squared. This tells us that a squared is divisible by 5, and therefore, O itself must be divisible by 5. So, we can write it as 5 times some integer k. Substituting back, since a equals 5k, and a over b equals square root 5, then a squared equals 25k squared, which equals 5b squared, as we saw earlier. Now, because a squared is divisible by 5, b squared must also be divisible by 5, which means that b is divisible by 5. But here's the problem. If both a and b are divisible by 5, then they share a common factor of 5. That's a contradiction because we initially assumed that a and b are coprime, with no common factors other than 1. So this contradiction proves that the initial assumption, that square root 5 can be expressed as a rational number, is false. Therefore, square root 5 must be irrational. Let's break down this proof step by step. First, notice that if 3 plus 2 square root 5 were rational, then, since a and b are integers, the expression frac 1 2, frac ab 3 would also be rational. This is because the difference of two rational numbers is rational, and dividing by 2 preserves rationality. Now, since this expression equals square root 5, it would imply that square root 5 is rational, but we know from earlier that square root 5 is irrational. This contradiction tells us that our initial assumption, that 3 plus 2 square root 5 is rational, must be false. Therefore, we conclude that 3 plus 2 square root 5 is irrational. Additionally, if we suppose it were rational, then there would exist 2 coprime integers, a and b, with b not equal to 0, such that 3 plus 2 square root 5 equals frac ab. But this leads us to a contradiction because it would imply square root 5 is rational, which we already know is not true. So the key takeaway here is that assuming 3 plus 2 square root 5 is rational leads to a contradiction, confirming that it must be irrational. So based on this reasoning, our initial assumption turns out to be false, and therefore, 1/square 2 must be irrational. Now, because b a is rational, and both a and b are integers, this implies that square root 2 is rational as well. But here's the catch. We know from earlier that square root 2 is irrational, so this leads us to a contradiction. In other words, if we suppose that 1/square 2 is rational and express it as a fraction, with a and b being coprime integers and b not equal to 0, then we arrive at this contradiction. This kind of proof shows us how assuming rationality for certain irrational numbers can lead us to logical inconsistencies, which in turn confirms their irrational nature. And this is a key concept in understanding the nature of irrational numbers. It's about carefully examining our assumptions and seeing where they lead us. So let's look at the key idea here. The denominator is of the form 5 raised to the power m. When that's the case, the decimal expansion of the fraction will be terminating. This is because the prime factorization of the denominator only involves 5s, which means the decimal will come to an end after a certain number of digits. Now, applying this to our example, 13 divided by 3125. Since 3125 is 5 to the power of 5, the denominator fits this pattern perfectly. Therefore, without doing long division, we can confidently say that this fraction will have a terminating decimal expansion. This concept is really useful because it helps us quickly identify whether a rational number will have a terminating or a repeating decimal just by looking at its denominator. It connects directly to the overall theme of understanding the nature of rational numbers and their decimal representations. Now, let's look at the key point here. When the denominator is of the form 2 raised to the power of m, which means it's a power of 2, the decimal expansion of the fraction will always be terminating. For example, take 8, which is 2 raised to the power of 3. Because 8 is a power of 2, any fraction with 8 in the denominator will have a terminating decimal expansion. So when we consider the fraction 17 over 8, or 17/8, this fits right into that pattern. Since the denominator is 8, or 2 cubed, the decimal expansion will terminate. Specifically, 17 divided by 8 equals 2.125. This concept is important because it helps us quickly identify whether a fraction will have a terminating decimal just by examining its denominator. It's a fundamental idea that connects the structure of the denominator to the nature of the decimal expansion, which is a key theme in understanding rational numbers and their representations. So based on our previous assumptions, we see that they turn out to be false. This leads us to conclude that the expression 6 plus square root 2 must be irrational. Now, since both a and b are integers, the difference, a b6, is also rational. And because a b6 equals square root 2, it suggests that square root 2 should be rational as well. But we know from earlier that square root 2 is irrational, so this is a contradiction. To put it simply, if we assume that 6 plus square root 2 was rational, then we could find two coprime integers m and b, with b not equal to 0, such that 6 plus square root 2 equals a b. From that, it follows that square root 2 equals a b6. This chain of reasoning shows that assuming 6 plus square root 2 is rational leads to a contradiction, which confirms that 6 plus square root 2 must indeed be irrational. This ties back to the overall theme of understanding the nature of irrational numbers and their properties. So here we see that our initial assumption, that 7 square root 5 is rational, is actually false. This means that 7 square root 5 must be irrational. Now, to understand why, let's consider the other part of the argument. If we suppose that is rational, where a and b are integers, then it follows that square root 5 should also be rational. But we know from earlier that square root 5 is irrational, so this creates a contradiction. This contradiction tells us that our assumption that 7 square root 5 is rational cannot be true. Therefore, 7 square root 5 is irrational. Now, just to connect the dots here, if we were to assume 7 square root 5 is rational, then we could write it as a fraction, a b with coprime integers, where b not equal to 0. From this assumption, we could derive that square root 5 equals a/7b, which would imply that square root 5 is rational, something we've already established as false. So the key takeaway is that assuming 7 square root 5 is rational leads to a contradiction, confirming that 7 square root 5 must indeed be irrational. This conclusion fits into our overall theme of understanding the irrationality of certain roots and their multiples. Now, let's look at the decimal expansions of the rational numbers from question 1 that have terminating decimal expansions. Remember, a rational number has a terminating decimal if its denominator, after simplification, contains only the prime factors 2 and 5. For example, the fraction 13/3125 simplifies to a decimal that stops after a few decimal places, which is 0.00416. Similarly, the fraction 17/8, which is 17 divided by 8, equals 2.125. Notice that in both cases, the decimal expansion ends cleanly without any repeating pattern. This is a key point because it highlights the fundamental link between the prime factorization of the denominator and whether the decimal expansion terminates. Understanding this helps us quickly identify which fractions will have these neat, terminating decimals, and it ties into the broader theme of understanding the nature of rational numbers and their decimal representations. So, whenever you're working with fractions, always check the denominator's prime factors. This can tell you a lot about how the decimal expansion will behave.